Recording is on.
Okay, so Tina Lani, want to start? Let me share my screen first. Entire screen, yes. Okay, so here we go. She's sleeping. Okay. Computational thinking and problem solving. So, what is computational thinking? So computational thinking is a structured approach to problem solving that enables us to one, understand complex problems, two, break them down logically, and three, design solutions that can be executed by a computer or a human. So first of all, you have a project, a problem, right? You have to be able to break it down. No, first of all, you have to understand that problem. Then you break it down and then you design a solution, right, which can be executed by a computer or a human. Okay, so computational thinking is not about coding. So coding is just one way to express computational thinking, right? After doing all the understanding, breaking down, coding can come at the last end, which is just a way of doing it, of expressing it, right? Because you could still express it in a different way. Your end result must not be a code. Are we there? Why computational thinking matters for software engineers, writing scalable systems. Are we there? The software engineers. So writing scalable systems, that systems which can appreciate as much as many people as possible, as many things as possible. You get it? You don't just want to. I mean, it's sure that some softwares that while building, um you have in mind that it's going to be used only for maybe elite, a small group of people. But most of the times, while you're building something or when you're going through a project, while you're implementing a project, you want it to be used by as many persons as possible. Yeah. Maybe you test it with just a little group of persons, but once you put it out there, you don't know how many people are going to have access to that. So while building your applications, while developing them, you want to make them scalable so that as many persons as possible can use them at the same time. For example, look at WhatsApp, right? I mean, it's everywhere. Can imagine how it is that people can use it at the same time, as many people as that. I mean, that's cool. Designing clean APIs. We're going to see what APIs are, right? Application programming interfaces. They help you do what? Connect between different services. Like maybe help with the back end, whatever back end language you're using, you need to be able to connect to be a database. You have to after developing your back end, you have to connect your back end to the front end. You need to create inter APIs for that. If let's say you're building an application which needs monetary services, right? Let's say you want to use Momo in your application, you need the Momo API, right? You need other things like the external services which you want to integrate into your application. You need APIs to be able to form that bridge. Are we there? Avoiding over engineering, obviously. So all this thinking, the computational thinking and the rest, understanding, breaking down, everything is so that you can come out um with a solution which is as minimal as possible. Don't know how von Neumann thought before even come out with that simple stuff, right? We are seeing it as very simple, but maybe that guy took years to come up with that. Hmm? Yeah, that's it. So then debugging complex bugs. So yeah, after building your site, your services and the rest, sometimes we experience bugs. So you will not just dive into it like that. You have to sit down, understand what's happening, break it down, and come up with a solution. Okay. Then for data professionals, designing data pipelines. So you guys are going to see what data pipelines are, right? Yeah, maybe where you fetch the data from, getting it APIs and all those kind of things. Yeah. Cleaning and transforming the data after getting the data. There will be most at times there are things which you don't need, right? So you need to know how you clean them, sort them, all of those things. Then optimizing queries to maybe databases, right? I mean, once you get the data, you have to store the data somewhere. For you to use the data, you need to write queries to wherever it's stored, right? So you have to get your query should be as efficient as possible so they can be fast enough for user requests. Are we there? Then identifying meaningful insights. So I mean computational thinking at the end of the day, the goal as a data analyst or whatever is to come up with what meaningful insights from the data. You won't just look at the data and come out with it, but you have to, no matter how the form of the data, you have to be able to reason it out, break it down, understand it, interpret it, and then you come out with something. Okay, note strong computational thinking results to what? Fewer bugs, better performance, and cleaner designs. Take note of that. So that's to say, if we have a problem right now which we want to solve, we won't just go straight to maybe a computer to start coding, because most of the times when I just tell someone that okay, we want to build this app, let's say build a app which can help people to book for let's say the next cohort, right? You just go directly to your machine and start coding. Now what are you coding? Doesn't make sense, right? Why you do that anywhere they'll see like an amateur, it's like you don't know anything, obviously. First thing you have to sit down and think. The thinking process can even go for 1, 2, 3 days, depending on the complexity of the task, right? Yeah, the computational thinking stage, which is going to help you to avoid what? To avoid bugs, obviously, and bring about fewer bugs, better performance, and cleaner designs. Any question?
Everybody just silent.
Right?
The brain is clocked.
Let's continue. So the the four pillars of computational thinking. One, decomposition. Definition. Decomposition is the process of breaking a complex problem into smaller, manageable sub problems. So breaking a complex problem into smaller, manageable sub problems. Are we there? Hmm? I mean, in general, I would say, is it decomposing? Yeah, decomposing something, right? It's like you're breaking it down, right? Okay. So why it's important? So reduces cognitive overload. You don't just want to look at it as a big process, but if maybe you break it down into sub processes and take handle one at a time, I mean, it at least you're not overloaded. Your brain is not overloaded, right? Enables parallel work. Parallel. What do you mean by parallel work? Yeah, what's a parallel work? Can anyone
Enables
parallel work?
Enables
Any idea?
parallel
Yeah.
means you can work other things,
Multiple things at the same time.
multiple things at the same time.
Exactly. For example, let's say we are a team, right? People can break down or decompose our problems like that. I can say,
She
okay,
handles yes and
exactly. Yes.
she
Hmm. That's clear, right? Okay. Makes debugging easier. Obviously, if you're handling your handling, if there's an issue, you can focus on that particular thing which you're handling, right? Let's say, oh, you have an issue after actually even coming out with everything. You can know that okay, due to the fact that we decomposed everything, you know, okay, this issue might be coming from this part, right? I go only to that place and handle that issue. I don't need to touch this one, touch that one, touch before I even know where the issue is coming from. Then encourages modular design. Yeah, modular design is the fact that you can have different modules. One module doing its own thing, the other module doing its own thing. That at the end of the day, you unify it to get one general product. Okay, example. So in a data analyst perspective, yeah. So build a comprehensive analytics dashboard. So that's the problem, right? Build a comprehensive analytics dashboard. So you can decompose it into. Let me see. I hope I'm not muted. Okay. So you can decompose that into one, collect raw data. Two, clean and pre-process the data. Number three, define metrics. Four, design dashboard layout. Five, implement visualizations. We all know what a dashboard is, right? Hmm? So I think you guys should be can be picturing out what we're talking about here and why it's divided or decomposed into these different steps. Then after you validate data accuracy. So yeah, you obviously need the data. That should obviously be the first step, right? Collecting the raw data, cleaning it, like we said. Yeah, I've gone and gotten data from this source, from that source, from that source. It's just like if I give out questionnaires, right, to gather data. At the end of the day, I won't just trust that every data is what I need. Hmm? I will come out, go through them, like I said, clean and pre-process. Hmm? Yeah, before define metrics. I don't know what it means in the data analyst context. But it could be like, okay, maybe based on the dashboard you want to build, right, you need to have this particular thing for the dashboard, this particular one, so that's all. Then you obviously after you know exactly what you need for your dashboard, you should design the layout. Huh? About designing the layout, you start implementing what is needed or what we have to see on that dashboard. And then validate data accuracy, whether what you actually get actually gives you what you're expecting, right? Yeah, or what you actually see is what you're expecting. That way. Okay, now an example for software engineers. Let's say you have to build an e-commerce platform. You know what an e-commerce platform is, right? Yeah. You know what commerce is?
Like Amazon, online market.
Yeah, online market. Okay, so you have to build an e-commerce platform. So you can decompose it into what? So like the sub parts, like what do you need? Say okay, there'll be user authentication to authenticate users, right? You can say okay, there'll be a product catalog where you store all the different products that you need for that e-commerce or that the user is going to find right in the e-commerce site. Mm. There'll be a shopping cart. No, my shopping cart. Like let's say you go to a mall, like that or that basket or whatever. Wherever you put your stuff. Yeah. There'll be payment processing. But you know what my payment processing, right? Mm. Yeah, like based on how many things you have bought, what is going to be the amount they are going to pay. Order management. Order management. What do you mean by order management?
Like on e-commerce website, you can order something that has to be maybe delivered to you, or maybe you're shipping to someone else.
Exactly. Notifications. Well, that was in case you want notifications for the site, guys. The notifications are very important. Exactly. So you add it there. So you have decomposed like it's a whole large problem or project, right? To build an e-commerce platform. They'll be like, okay, yeah, that's it. But an e-commerce platform is composed of what? There has to be authentication, maybe like we saw shopping cart, product catalog, all of those different parts. Then you can say, okay, you can, if you have a team, right? And say, okay, you're working on user authentication, you're working on shopping cart, you're working on product catalog, you're working on this, you're working on that. And when we're all done, when all of those are working the way we want, it creates now what? Your e-commerce platform or website. Are we there? So we sort of decomposed it into different processes or different problems. Yeah. A common beginner mistake is breaking problems into steps instead of logical components. So logical components mean a conceptual building block representing a system's functional parts, defining what it does, so the features, operations, or data, rather than how it's physically built. So in this stage of decomposition, we're not actually looking at how it's going to be, right? We're looking at what it does. So we're decomposing it based on the features or the operations that are being carried out. Just like e-commerce site is there. So okay, there'll be user authentication, there'll be this, there'll be that, based on those different features that we want or that our platform is going to be is going to handle. That will not okay. If we solve all of these individual problems, we're going to solve the general problem. Pattern recognition. So we're under the four pillars, right, of computational thinking. So I've talked about decomposition. Now pattern recognition. Okay, after decomposing them into different components, subcomponents. Now talk about pattern recognition. Pattern recognition is identifying similarities, trends, or repeated structures across problems. Why it's important? Enables reuse of solutions, reduces development time, improves consistency, helps predict future behavior. So let's say we have um, um, when you go to a website, right, you mostly notice that um, the login screen and the create an account screen are mostly the same, right? Hmm? So so that's a pattern there, right, that you can identify. So okay, it means if I can create the login screen, then I can obviously create an account screen. Hmm? So it will not make sense if you tell me that you have created an account screen, but you cannot create a login screen. It will be strange. Okay, now an example: software engineering, website login, mobile app login, API token validation. So all follow the same authentication pattern. So you can reuse the whatever authentication you're using in one on the other one. No one by authentication, right? No one by authentication. Um, when you come to that login process that occurs before entering your account, that's authentication. Like exactly, let's know who you are.
Verify
Yes,
it.
that's exactly. Hmm? Okay,
So please, what are tokens?
API token validation. Um, when you log in, right? We're working between, let's say, two different services. Because when we talk about API, we're talking about different services. I don't want to say back end and front end. Let's say different services. You get it? If I want to have access to this service, after my authentication, it has to give me something to recognize me if next time I want to have access to that service again. So the token, right, mm,
Mm-hmm.
is the thing that you say, okay, it carries my identity, such that if I want to have access to that service again, I can use that token as my ID card. So token validation, it validates it that yes, this guy has authenticated, this guy has access, can have access to this service. Are we there? Mm. So doing the authentication stuff, right? I don't know how to keep saying back end. But when you log in, your backend has to send a token. You get it? So that so far as you're logged in, you always use that token to show that hey, I'm the one. It's like your ID. Just like that.
Okay.
So like it generates an ID for you. Then anytime you want something, you show it. It's okay, take. You show it, take. So that's it. Okay. Example data analyst. So sales trends across regions, customer churn patterns, seasonal spikes in traffic. So recognizing patterns helps build predictive models. So at the end of the day, I just want to say there's a pattern between these three, right? Between these three, which if once recognized, it can help to build all the three. So let's say if I create one of these, so sales trends across regions. If I'm able to create this, then I should be able to use the same knowledge to analyze this one and to analyze this one. Okay, then abstraction. Abstraction. So the definition of abstraction. So decomposition, pattern recognition, then abstraction. Okay. Abstraction means focusing on what matters and ignoring irrelevant details. So, in summary, abstraction hides complexity and exposes only what's necessary. Are we there? Example: user model in database. So, ignored, hide, hair color, favorite food. Included, user ID, email, registration date, account status. Okay. Okay. So let's say you're creating a, like, based on that's for, okay, software and data. Let me see. But it feels like this was more of data, right? What about the database? So you have to store user attributes. You get it? It's obviously, yeah, the user has a height, a hair color, and all whatnot. But if you don't need that, they don't need to get it. Just have to store what you need. Like, forget about the noise and get just the meaningful, the relevant parts. So user ID, that's what you need. Or if you store all of this data when fetching from a database, it's not if I must fetch everything and give to whoever is coming to ask for it. The person doesn't even need to know I have height, I have hair color, I have favorite food in my database, guy. If the person needs just their ID, I give them just their ID, maybe their ID number or whatever. If the person needs just their email, I'll give them. If the person needs just their registration date, I give them. Account status, I give them. Exactly.
Yes.
Yeah. See, we're really tired now. I skip from Tina to you. uh, software engineering example. So when using a function sort list, you don't care how sorting works, right? You don't care how the sorting works or how the what the function, how the function is working. You just only that it works, right? Just you're just expecting an end product. Does it work? Yeah, it does. You not go and open the sorting function and be checking how does this thing work. I must know before I continue. No, it has done the work. Continue. It just
What they do the function.
exactly just like going to the ATM machine, I slot my card, get my money and go. I'll not be like, I'll bring schools. I must check how this is what this thing is doing inside.
Them bringing money inside this thing.
Okay, data engineering. You treat a data pipeline as input, the input transform and the output, right? So without worrying about internal implementation at every stage. Okay. I don't know. Data guys will handle that way. When you guys will do a data pipeline, I'm sure you see what they mean here, right? Yeah. But at the end of the day, it just means that, I mean, maybe there's a function that does the input, the output, and the processing or transformation, and just gives you the output, guy. You don't really need to know, is it how is this how is it doing this? I must check and know. Levels of abstraction. So hardware, operating system, runtime, libraries, application, logic. These are levels of abstraction in the computer as a whole, right? So um, the normal, let's say, there's some people that is even to that actually saw maybe the CPU or even saw this where the CPU is found and all those kind of stuff, right? Or maybe um even saw the hard drive that's inside there. In fact, saw those things are inside that box, right? Is that those are like complexities that have been hidden. You're just seeing the box, it's black and it's cool. some are white, some have good designs and everything. So it's just like it blinds you from the those other part, the complex parts, right? But once you open it, it's like wow, a whole world on its own. This device is here, this one is here, this one is here. Okay, talking talking about the chip that's inside. You see the small chip, and I mean just there.
Small but powerful.
Exactly. Now with what you saw that it's like a whole universe on its own. You can actually, I mean, you can study that stuff for 2 years and you might not still understand what's happening inside. Yeah. So that it's at this abstraction in the hardware level. Then operating system. I mean, talk about operating system here is that this one right here was seeing just the shell, but I mean in the background there's a whole kernel doing this, doing that, doing that, doing this. Even the applications they don't even the applications themselves are inside the application softwares. They have to interact with it using what? System calls. Means they only know that okay, I'm just sending a message. They don't even know this and whatever is behind there doing it. So you see the abstraction between the different layers. That's why we have a user mode and a kernel mode. User mode, yeah, we're seeing all the beautiful stuff, pictures and everything, but behind there, computer is seeing ones and zeros. Mm. Okay, runtime, Java virtual machine, Python and the rest. So after the operating system, we have runtimes. When you program your code and everything, what happens? Each, let's say, programming language comes with its own stuff. This one uses an interpreter, that one uses compiler. When you do it, it sends it through it before it wants to go to even the operating system. Are we there?
Yeah.
We go to libraries. Why coding? Use a library, use this library, use this library. You don't even know what is inside those libraries. And just use it. So you just see there's abstraction at every level. Then the application logic is set. Even you yourself while writing, you create functions and keep them somewhere and you're using them. Are we there? So each layer hides the one below it. Yeah, that's very true. Because yeah, just like we talk about operating system, it's like it just cloaks you. Yeah, you don't even, it hides the hardware, right? Yeah. Anything has to pass through for it's the one who knows what to do with the hardware. Okay, algorithmic thinking. So that was which one was that? This was abstraction, right? Now let's go to algorithmic thinking. So algorithmic thinking now has to do with what? Creating a clear step by step. So these are all under computational thinking, right? Hmm? Yeah. So now creating a clear step by step procedure to solve a problem. Let me check this recording. Okay, still recording. Okay, so creating a clear step by step procedure to solve a problem. A key characteristics here or key characteristics of a good algorithm is finite, which means it ends, right? Let's say I want to well they mostly use the the example to make tea. So I say give me an algorithm to make tea, right? So at the end of your algorithm, I should be, or if I follow your algorithm or your steps, I should get my tea, right? It means it should end somewhere. Mm? It should end somewhere. It should not take, I don't know, it should not be infinite, right? It should end somewhere. It should be precise, no ambiguity. Don't take me here, take me, take me here. Whereas it's a direct step or a direct pattern to follow. It should be correct. yeah, I want to have an end result in mind, right? To get tea. You should not give me steps which I follow and instead get soup instead of tea. Mm. You should be efficient. Yeah. You should do the work, right? You should do the work and with as less time as possible. Efficiency has to obviously do with a lot because the space and time efficiency. Like when we come to efficiency, when you talk about speed, talk about time, the main thing is you should do the work as fast as possible using less space if it can, right? Okay, example, sorting client names alphabetically. So that's okay. Steps, compare the names. So step one, like compare the names, decide the order. Okay, so if I don't get it here, compare the name, then decide the order. I think order is like
Maybe
maybe
from Y to A.
exactly or from
A to Z.
A to yeah or from B to A, yeah. Or is it ascending order or descending
Descending.
order, right?
or alphabetical order since it's
Okay.
linked.
Yes, yes. Mm-hmm. Yeah. So you compare them, you decide which one, how the order, then you rearrange it, right? Whether okay, no, based on this, it means based on this order which you want to use, then this guy should come first. Are we there? Then repeat until it's sorted. Is it clear?
It's clear.
Just like that.
Why are you laughing?
Come on now.
Why is he laughing? Because of him that we are all laughing.
Okay, let's continue. Software engineering focus. Okay. So time complexity, O over n, O to n, log n, space complexity, edge cases. Like software engineer, this is what you'll be focusing on when it comes to complexities. You're checking all of these, the time complexity, how long does it take to actually do the work? Because the way I make tea is not the way you make tea, it's not the way she will make tea, right? Mm? And each of those different ways have their own time which will take to make it. That's clear, right?
Space.
Yeah, and space. So now we're going to space complexity. Maybe my own needs just a kettle to make. Maybe I own need a pot. Maybe another person only a drum. I don't know if how you make
Human
your
might
own
not even
tea.
need heat at all.
Right? Yeah, so that's it. Then the edge cases. What do you mean by edge cases here? What do you mean by edge cases here? Does anyone understand by edge cases? Like, mm, how do I put it? How do I put it? Worst case scenario.
Yep.
It was. So, come again. Let us do something. Let's talk about worst case scenario, best case scenario, right? Like, what's the minimum thing that we need to actually make a tea? Really make a tea, make tea. uh, yeah. Then if we want to really make it like I don't know, maybe make it for how many people too, right? Because number of people, all those kind of things, right? Then from there you can get different scenarios, different cases, different edge cases, right? Yeah. Okay, data analyst focus. Data size, obviously based on your data size too, you get the algorithm that you need, right? Based on how accurate you want it to be.
It's 2 cubes. No more, no less.
Handling missing or noisy data. Like how I don't know, maybe it's
Maybe when there's more water, how, when you mistakenly exceed the number of cubes of sugars, how do you adjust that?
Add more water.
Add more water. Exactly.
So now you see that those are different things that you have to actually check, right? If you're doing those things, or if you are writing an algorithm. So you say it's not just the straightforward thing they're doing, but now, yeah, in case of this, like you have taken all of those different things. Like remember, we're thinking this computational thinking. Want to finish all of these and actually fit the computer or program the computer to solve our problem. Computers are dumb, as you need to give them every little thing. Yeah. Okay. Pseudocode. Okay, this number four. Pseudocode. Pseudocode. So like
So
it's
physical is more foundational code.
okay. It means I should be getting, I should be getting input from you guys now.
More like not even getting it, more like just
Just
saying
keep.
the next. Yeah.
Okay, let me just read your list now. Eh, okay, I'll not explain. Just get a go. If you had to answer the question, ask.
Then give us fast.
So pseudocode, the bridge between thinking and coding. What's pseudocode? Pseudocode is language agnostic. I had to ask, what do you mean by language agnostic?
Oh,
It was not there.
Language.
What do you mean by language agnostic? Please say it was. Okay. No, that was not there.
By using plain English or a language to describe the problem.
So it does not depend on a specific language, right? Can use can yeah, the main thing is do it in a way which people
Do it in a
understand.
language.
In a language which people understand, obviously. Right? Because we cannot all be speaking or understanding English like come and do French. It will be bizarre. What are you doing? Yeah, but it's not depending on a specific language. No matter the language, it will be the same steps, the same way. Let me put it like that. Oh, not really necessarily, but it does not depend on something. Yeah, on a specific language.
You understand, or people around understand.
Yeah, yeah. So see, yeah, general stuff which all of us can see and understand what is happening. Yeah, but it's not like something which okay if I say this in French, maybe the Anglophones will not understand.
Even if you start writing the quotes now, Python, blah blah blah, you will not
Exactly.
understand what
Yeah, yeah. You guys, yeah, you might not understand. If I put in C, put in Bash, for languages like that, right? But this one, it doesn't depend on any programming language. No, just put in a normal human readable languages. What we should get. Human readable. That's it. Structured like code. Used to plan logic before implementation. That is that you are not still in the implementation phase. You're still in the design phase. Yeah. Then if your pseudocode is weak, your code will be messy. Yeah, garbage in, garbage out. Why pseudocode matters forces clarity of thought. Just writing down the processes allows you to think before even going to start coding. Makes logic reviewable. Reduces coding errors. Improves communication in teams. Example, sorting algorithm, pseudocode. So start for each element in the list, compare with next element. If the current element or if the current is greater than the next, then swap them. Repeat until list is sorted. N. I mean, this is clear. We can all see the different steps. I mean, it's readable, everything, right? Data cleaning task. Load raw data set. Remove duplicate records. Handle missing values. Normalize numerical columns. Export clean dataset. Yeah. So it starts somewhere and ends with what you want, right? Okay, that's clear, right? Okay, computational thinking in real world workflows. Software engineering workflow. Yeah, I give you the feature, my problem that I have. Yeah, the software engineer should be able to decompose it right into different features. Okay, you're not just going to, I don't know, I don't even know how, I don't even, I don't even know how to think of it like I'm building something, I don't know, a whole like that. You must decompose it down, right? I mean, programming languages are even structured in such a way that you can even, I don't know, you must decompose something to actually build a larger unit. Recognize reusable patterns. Exactly. If you decompose it, you realize that okay, maybe this one and this one and this one they are similar, which means maybe the pseudocode I use here or the code I use here
Can be
can
reused.
be reused. Abstract system components. I don't know, we want this at the end of the day. Don't You must not show me this all of these other parts. No, just show me what I need. Um, Design algorithm. So we start all of these parts, all of these pieces are in just like a thinking phase, right? You go, you design the algorithm, like you write it down step one, step two, step three, step four, depending on how many steps you require to finish it. So you write down your steps, you come and check them. Time complexity. How much time, if I'm using this, is there a better way I should have approached this thing in terms of time, in terms of space? Check all the edge cases. Then when you are like, okay, I think I can go with this algorithm, right? Like I said, there are many ways to do one thing, right? So that's why you should sit down and think, rethink, rethink, evaluate, reevaluate, yeah. And then now, once you have settled for one algorithm, you write the pseudocode. So it's not necessarily for the whole problem, obviously, right? For the different components, that's why we're decomposing them down into several components. So you take this one component, you write the algorithm to actually build that, right? You write the pseudocode, then you implement. Just like that. So pseudocode and then implement. Once you done with the implementation, optimize. I mean, there's no perfect product, right? You write it now, tomorrow you come and see bugs. You have to keep maintaining. Even WhatsApp, you're still maintaining WhatsApp. Still get WhatsApp updates. Yeah. Data engineering workflow. So one, break pipeline into stages. Two, identify recurring transformations. Abstract data models, define processing logic, write pseudocode, implement in whatever you're implementing, Spark or SQL.
Spark is your platform.
No,
It's a different.
like a language, right?
Oh, okay.
I mean it. I mean it depends on what you're
There's no
doing.
mail. It
Yeah,
just depends on what you
yeah. What you're doing, what you know to, which one you know to. Yeah. So the fact that you're using this one does not mean you could not use the other one. Yeah. Because maybe that's the one you know at that moment, right? Yeah. Then yeah, monitor performance too. So at the end of after implementation, there will always be that last step which is to maintain whatever you have done. So you see that only the design takes all of these, or let's say this, because no, you can say all of this, eh? But most of the time, the first stages are more of gathering your data. Yeah, then you design it, then you implement. And most of the times, you can even break down this implementation stage right into the development and testing, right? After actually writing, you have a test, right? You test before now. If you are deploying it to the site, you deploy and all the rest, then you start monitoring and maintaining. Common mistakes in computational thinking. So jumping straight into code, over abstraction too early, yeah, ignoring edge cases. In case we have 500 users, how is it going to be? In case, I mean, you have to get a balance, right? Everything. Not validating assumptions. Yeah, I mean, why? That's why all those processes matter. Within it, you're going to be having in case those assumptions and everything. Don't just
Dismiss them.
yeah. So writing big algorithms that lead to nowhere. I actually use them. Like sometimes you actually write an algorithm, like you know actually go through all the different steps to be sure that it actually solves the thing that you're setting out to do. You just like every time and all this kind of stuff, you have to move to the next step. Find yourself going back and forth, going back and forth, and remaining in the same spot. Okay, exercise this. Why is everybody proud? Okay, breakdown. So breakdown online food delivery app. Online food delivery app. You know what I mean by online food delivery app, right?
Yeah.
Yeah, I like that. It's food, right? So let's break it down and see. How would you break it down? I mean, there's no correct way, right? It depends on
Actually,
exactly. So how will you break it down? Go ahead.
Okay, I think we first of all do like um, maybe a login page in case you have like a recurrent client.
So login page is one.
Notification from variety, you have more food varieties and all. You can have an order page.
Mm-hmm.
Catalog here is displaying
Menu.
the menu.
Okay.
Um,
Come again. Payment
Payment.
process. Yeah.
operation hours.